so this lesson here is continuing with the idea of a geometric sequence and now applying it to a geometric series, which really just means the difference between a sequence and a series is that a sequence is a series of terms in a row. Oh, I just said the word series. That's annoying. Anyways, a sequence is a list of terms in a row. A series is where you add them up. That's the only difference. Instead of just listing them up, the idea is you're adding them, adding some number of terms. And so a geometric series is where you're adding up terms that are part of a geometric sequence. And this is one of the rare times of the course I'm just giving you two formulas without explaining where they come from. And that's because they're not very easy to understand where they come from. The textbook does a decent job of explaining it. Honestly, I think you're probably better off just not worrying about it. But the textbook does explain it. But in general, both of these formulas here will tell you how to find the sum of any number of terms, n being the number of terms, for a geometric series, where t1 is the first term, r is that common ratio. And again, there's two different forms of it. All right, so the best way to get into this is just to try to use it. And so here I have an example of a geometric series, 100 plus 40 plus 16 plus, and so on. So this particular series goes on forever. And so as usual, we can call 100 term 1, 40 term 2, 16 term 3. All right, so I can also see my common ratio. 100 times what equals 40? Well, I can actually just see that that must be times 0.4. But you can also go 40 divided by 100 and get that same thing. But I can see my common ratio there. All right, so what does S at 4 mean, or S4, I should say? That means I want to find the sum of the first four terms. Now, I could use one of these formulas, but why don't I just look at my sequence here, or series, and just write down 100 plus 40 plus 16 plus, I just need to find one more. And to find one more, I just need to find what the fourth term is, which is going to be 16 times 0.4, which go to a calculator, you get 6.4. And I struggle to see how that's not going to be faster than using one of those formulas. And if you do this, you get exactly 162.4. And so that represents the sum of the first four terms. Honestly, pretty simple. The idea is very, very simple. I'm just adding up a number of terms. And in this pattern, in this case, adding 4 terms, that's it. Now, adding 20 terms, while I could continue this is where one of my formulas is much more useful. So I got 2. In general, if I look at this, this formula here is more useful if I actually know the last term I'm adding up. Because let's say I wanted to find the first 20 terms. Well, that means n must be 20, which means that term there would be term 20, the last term I'm adding. I don't know what the 20th term is. I could figure it out using what we looked at in the last lesson. But why don't I just use this form of it right here? Which, again, for this, all I need to know is the first term, which I know, the common ratio, which I know, and the number of terms, which I know. So I'm just going to use that form of it. And so in this case, it's going to be 100 times 1 minus 0.4. to the power of 20, all divided by 1 minus 0.4. Now, be careful when typing this into a calculator. I would generally recommend typing all of this first, finding what the numerator equals, and then dividing by this in brackets. Again, you just need to make sure your order of operations is correct on your calculator. But in this case, you should get about 166.67. So notice, compared to adding the first 4 terms, adding the first 20 terms actually doesn't make a big difference. It's only about an extra 4 more compared to the first 4 terms. And that's because every time I'm going to the next term, they keep shrinking. Like they're getting multiplying by 0.4. Each value you can see is getting smaller. So it's not really that surprising that adding another 16 terms doesn't actually make that much difference to the total sum. So what if I add the first 200 terms? Well, same idea. Use the same formula as before. Again, be careful how you type it in. I recommend against trying to type this in all at once on your calculator, but I assume you know how to use your calculator. And if you do this, you get something that is extremely close, but not exactly the same as 166.6 repeating. And so notice, after a while, these two numbers, I mean, if you just round them to the nearest whole number, they seem to be exactly the same. They're not. I mean, I know they can't be the same. I know if I'm adding 200 terms compared to 20, I know the two values actually can't be exactly the same. I don't care how many decimals I see in my calculator screen. I just logically, I know these two can't be the same, but they are extremely close. That's an important idea leading into actually to the next lesson. So they are extremely close, but not exactly the same. And that's simply because by the time I get to the 200th term, by the time I get to the 20th term, I'm adding such small numbers, and they keep getting smaller, that adding extra values is making less and less and less of a difference. All right. So with that said, let's look at a different series. This time I have term 1 being 1/27th, term 2 being 1/9, term 3 being 1/3. I skip a few, I don't know how many. 729 is the nth term. So first I can clearly see that, especially because 729 is so much bigger than my first few terms, I know that my common ratio is bigger than 1. I know that each time my terms are getting larger. So how much? Let's figure out my common ratio. 1/27th times what equals 1/9? Perhaps you can see it, but it's probably not that obvious. Or you can go 1/9 divided by 1/27th. In the end, you should get exactly 3. Each term is getting exactly 3 times larger than the one that preceded it. All right, so I want to find the sum of this whole series. Well, I'm not told anything else but this. So let me first write down again the two sum formulas I've given you, and then see how we can approach this. There's always more than one way. OK, so if I look at the first equation right here, at some point I need to find n, the number of terms. So how could I find n? Well, that's similar to the sort of a question we would have seen before. Essentially, I know 729 is the nth term. And so I could use, but I know it's part of a geometric sequence. And so I could use this formula from last day, Tn equals T1 times r to the n minus 1. I could use that to figure out what n is. And then I could plug everything else in, because keep in mind I do know the first term, I do know the common ratio. But why don't I just use the other form of the formula? Because here I actually don't need n. If you look at it, nowhere here for the right side of the equation do I actually need to know the number of terms. I don't need to know how many terms I'm adding up. It's kind of a strange idea. But if you look here, all I need to know is the first term. I need to know the common ratio. And effectively, I need to know the last term. Tn is like my last term I'm adding up. So I don't actually need to know how many terms I'm adding up to find the sum of them all added up. All right, so that said, let's use that one then. And so in this case, the sum of the first n terms, I don't even know how many it is, but it doesn't matter. The first term is 1/27. Minus 3 times the last term is 729. All divided by 1 minus 3. And again, many ways you can use a calculator for this. Just be careful. But then it's just a matter of just typing stuff into a calculator, which I care little about. And so this comes to about 1093.5. That said, if you were to do it this way, I'd have to first, again, find the number of terms, and then I could substitute it in. I should get the same value. I really say what links these two equations together is that formula, Tn equals T1 times a to the, sorry, not a, bad me, times r to the power of n minus 1. And one of our group problems, if we have time, is about showing how algebraically how these are connected. That said, though, in this case, the formula on the right is far more useful. All right, let's look at this problem. Determine the value of a, really the first term, in the following geometric series. OK, so a is the first term. I'll just even label it T1. So a is the T1, I don't know. Then I skip some terms. And then I have negative 1,000 plus 500, but I know it equals I know it equals 4,168. So how can I find the first term? Well, one thing I would do right away is figure out what my common ratio is, because I can see the common ratio right here. I don't know what, I don't know what these two terms are, although I am going to label this as Tn, right? That's kind of a common thing. That's my last term, so I am going to label that as Tn. And so if I want, I could label negative 1,000 as the term before Tn. And so how would I label the term before Tn? That would be Tn minus 1 if I wanted to. That said, regardless of that, I can see the common ratio from negative 1,000 to 5,000. I must be multiplying by negative 5. I can see that right there. So that's always going to be important. So now let's think about how I can find the first term. So if I look back again at these two formulas that were introduced, they both involve the first term. All right. But again, the one on the left, I need to know the number of terms. The one on the right, I don't. And if I look at the one on the right, I know everything but the first term, right? A is what I'm trying to figure out, T1, but I know the common ratio now is negative 5. I know the last term I'm adding up is 5,000, and I know that the whole thing equals 4,168. And so everything here I can either know or which means except for the first term, which means I can figure that out. So let's substitute everything in here. So I have 4,168 equals A, or the first term, minus, now we got to be careful, minus negative 5 times 5,000 all over 1 minus negative 5. So at this point, as long as we're careful, there's not much to it, but there's a lot of negatives going on. So what I want to do first is just clean this up a little bit and say, because I don't like all those negatives, 4,168 equals A plus 5 times 5,000, which is 25,000, divided by 1 minus negative 5, same as 1 plus 5, or 6. I like that better. Now, multiply both sides by 6, and really, at this point, all I have to do is multiply both sides by 6 and just subtract 25,000, and I get A equals 8. So I know that's my first term. And so again, these formulas for finding sums, especially when we're adding up terms we don't even know how many there are, the formulas are definitely quite helpful. But we need to put thought into which one we want to use. And it depends what information we're given and what's going to be important to us. OK, the last problem, the final problem, becomes strangely timely in these last little while. Before the spring of 2020, a lot of students didn't really understand what it meant for something to go viral, aside from something on social media. I think we all appreciate now that something going viral has to do with a virus originally, and that they can grow quickly. And the growth of a virus can be modeled with a geometric sequence or a geometric series, at least initially. And in practice, that means numbers can get large very, very quickly in a short amount of time, which again is something that I think the entire world now appreciates. And so what I have here is a graph. Now it's made up data, but a graph of showing the number of new cases of people infected by the flu over a 10-day period. OK, so again, on my y-axis, this is every day the number of new cases on that particular day. And the x-axis is the number of days. Well, we can really think of the number of days being the term number and the number of new cases being the term. So if I look at this, day 1, it looks like, it's hard to tell. Again, we have to kind of do our best job estimating, but it looks like this is about 2 cases. This is not much more. I'll say 3. This looks pretty close to 5. This looks, 7 or 8. This looks a little bit more than 10, so I'll say 11. This looks like, 17 or 18 or something. That said, I don't actually have, I'll keep doing this, but that's what I am, to be honest, doing far more than I have to. This looks about like 26. This looks just short of 30, so I'll say, just short of 40. So I'll say about 39. This looks just short of 60, so I'll say 59. And this looks a little bit short of 90, so I'll say 88. Okay, those are my rough estimates. Again, they're probably not exact, but honestly, they can't be that far off. So my first question is, how many people were infected by the virus in the first 10 days? Well, I could just add up all these numbers, and that actually might be faster than what I'm about to do. But I'm not going to just literally add these all up, although I could. However, of the two formulas, if I use this formula right here, the one I've actually been using more often today, if I use T1 minus R times Tn, all divided by 1 minus R, all I need to do then is I'll call Tn my 10th term, 88. T1 is my first term, 2. The common ratio, I don't know yet. But once I can figure it out, then I'll do that. And this will be quite important for the next question, which is how many people are infected after the first 20 days. Although, again, I could just continue once I find R, I could continue the pattern. So what's R? Well, one thing I could do, which I don't entirely recommend, is just pay attention to the first two terms. Because I'm not so confident about those two values. They're so close to one another. But it does seem to be about 1.5. OK, well, that said, what about 3 to 5? Well, if I go 5 divided by 3, it's about 1.6. OK, so fairly close. What about 5 to 8? If I go 8 divided by 5, you get about 1.6. 8 to 11. And again, I don't know if these numbers are exact. I get about 1.4. I'll do one more. 17 divided by 11, I get about 1.5. And so if I look at here, if I'm going to model this with an arithmetic series or sequence, I need to imagine these all being exactly the same. And they might actually be the same. In fact, they are exactly the same in terms of if I knew the actual numbers. And I only know that because I made the question and I made up the data. But they're not exactly the same, but they're all around 1.5. OK? So one thing I could do is look at this and just say, OK, I'll say R must be about 1.5. The key is I need to look at several of these to get a decent sense. I could, if I went one more, if I want 26 divided by 17, again, I get about 1.5. And the larger the numbers get, the more accurate I think my R value is going to be. And so, again, if I jump to a conclusion too early, I might have thought it's going to be closer to 1.6. However, another idea, which I kind of like better, is to do this. Let's look at the jump from here all the way to here. I feel pretty good that that last number is pretty darn close to 88. I feel pretty good the first one's pretty close to 2. And let's think about that. I can figure out R algebraically. And again, I'm still estimating, but I'll maybe a bit more accurate. And so in this case, I know if I go from 2 cases in a day to 88 new cases in a day, that took 9 days. 1, 2, 3, 4, 5, 6, 7, 8, 9. And so I know whatever this R is, which it seems like it's about 1.5. I know if I go 2 times R 9 times, I should get 88. So I know 2 times R to the power of 9 should be 88. So that's what I'm going to do right here. I know 2 times R to the power of 9 should equal about 88. And so I know I should get something close to 1.5. And so let me just divide both sides by 2, which means R to the power of 9 should be about 44. And now how do I find R? I want to find the 9th root of both sides. And the 9th root of 44 is about 1.5. I get about 1.52 on my calculator, so I'll just stick with 1.5. And really, this just kind of confirms that, yeah, what I was looking at before seems pretty good. And so either way, I mentioned 2 ways of looking at it. The main important thing is not to jump to a conclusion, especially if I actually give you real data, where you can't expect the R value to be literally exactly the same. But if a geometric series or a geometric sequence is going to be a good model, there should be some equivalent. There should be some equivalent to an R value that is roughly the same day by day. And I will say, when it came to the coronavirus, it definitely was in the first few months. There was it followed an arithmetic sequence incredibly closely, which is why it went from being just a few people to millions in a short amount of time. And I'll talk more about that later on. That said, let me actually answer this question. So the first 10 days, I can now use this formula right here, because now I know R is about 1.5. So let me just write here. I'll now say S of 10 equals the first term, about 2, minus about 1.5. I could put 1.5 too. I'll just stick with 1.5 times 88 divided by 1 minus 1.5. And if I go to my calculator, I get out about 260 people, which should be the same thing I get roughly if I just add up all these numbers I drew in red. OK, that was after 10 days. So according to this, because again, each day I want to add these up because these are the number of new cases each day. And honestly, when you look at reporting periods, how they report cases of the coronavirus, it's always the number of new cases each day. So it's, again, all of this I think is a bit more easy to understand than it would have been a year ago or more than that. And so you may assume now for the last question, in which I want to see the first 20 days, a common mistake is to think, OK, 20 is double of 10, so there should be about roughly double the people. Or maybe realize it's more than double, but it's hard to appreciate how much more than double it's going to be. So in 10 days, in total, 260 people were sick. If I add another 10 days, let's see how many people will be infected, according to this model. And it should be quick. If I want to find the sum of the first 20 days, I need to go same first term, same R value. And in fact, if you've read a fair amount about the coronavirus, they talk about what they call R naught value, which is essentially the same thing. It's how many times something is growing by, in a sense. That's it. I'm getting off track. And so I don't know, sorry, I can't use this formula. My apologies, because I don't know what the 20th term is. I could figure it out, but I'll use the other formula. Actually, I'll write down the general form of it first. So Sn equals T1 times 1 minus R to the power of n over 1 minus R. For this particular question, this formula is more helpful, because I don't know what that 20th term is. So sum of the first 20. So 2, 1 minus 1.5 to the power of 20 over 1 minus 1.5. So like I said, after 10 days, we got about 260 people. After 20 days, I've said it several times, it's going to be more and a lot more than double. But how much is a lot more than double? Well, after 20 days, if you type this in, you get about 13,297 people. That's a lot more than double. And that is the nature of geometric growth, or what we'll eventually start to just refer to as exponential growth. All geometric sequences are a type of exponential function, and the difference in looking into that is really what so much of this unit is about. But that is a feature of exponential growth or geometric growth, where it seems fairly small at first, but left unchecked, which is what happened with coronavirus, left unchecked and able to spread, it can go from being relatively small to immensely large numbers in an incredibly short amount of time. So with that said, I'm going to stop talking for now.